Hi guys, here is your lesson for piecewise functions. So piecewise functions are sort of exactly what they sound like. They are functions that are made up of lots of sort of pieces. And if you're not familiar with them, here this f of x and g of x are both great examples of what piecewise functions are. So they are sort of regular functions that are here, and they are split up on my graph or over my domain, and it gives you a specific sort of piece of where those functions belong. So for example, if we were evaluating these piecewise functions, here, if I wanted to evaluate f of 8, the first thing that I would need to figure out is which value this piecewise function sort of belongs to. And when I say which value, I mean which chunk of my piecewise function does this belong to. So if I look here, 8 is going to fall under the category of being larger than 5. So I'm looking here to plug my 8 in. So the absolute value of 8 minus 2 is going to be the absolute value of 6. So f of 8 is equal to 6. And f of 0, looks like 0 would fall into this domain piece right here, since 0 is smaller than 1. So 2 times 0 cubed minus 1. So 0 minus 1. So f of 0 is going to be negative 1. And f of 4 falls into this category here, being in between 1 and 5. So f of 4 is just equal to 3. So another nice example over here, g of negative 4, which piece of my piecewise function does this x value belong? And it looks like negative 4 is smaller than or equal to negative 2. So 2 times negative 4 plus 8. It's going to give me negative 8 plus 8. So g of 4 is equal to 0. G of 6 is a value that's larger than 3. So this is going to be the square root of 6 plus 3. So the square root of 9, which is going to give me 3. And g of negative 2, so negative 2, I can see here, if I take a look, I see negative 2 here, and I see negative 2 here. This is actually the piece that I will pick because x is less than or equal to negative 2. Negative 2 is equal to negative 2. So 2, negative 2 plus 8. This is going to give me negative 4 plus 8. So here I'm equal to 4. So piecewise functions are sort of exactly what they sound like. They are functions that are made up of separate sort of pieces or chunks of other functions, and they always have this sort of nice domain that's off on the end that tells us which chunk of my domain belongs to which piece of my function. So if I keep scrolling here and we talk about graphing piecewise functions, so here's a really nice example of a piecewise function that's graphed. So you'll look on your graph, these sort of dotted lines, none of these dotted lines would show up, and we would just be left with this nice sort of continuous graph that we have here. These pieces are here, these dashed lines are here to show you sort of the breaking points. So this is saying graph 2x plus 8 if x is smaller than or equal to negative 2. So this is my breaking point here. So this side of my graph will look like this, and this side of my graph will look like this. And we can see that if I were to, let's see if I can add in some kind of blank sticky here. If I were to cover this up here, there we go. Let's get this how I'd like it to look for just a sec. Bear with me just a sec. So from negative 2 over on this way, so everything over here looks like this x squared, and if I were to move this over to the other side, I am only, here you can see that I'm only seeing this, we can delete this now. I'm only seeing this value over here for all of my x values that are less than or equal to -2. So let's do a nice example. Let's graph this piecewise function. So the first thing that I want to do is take a look at my domain here, and I'm talking about x values that are smaller than or equal to 4 and x values that are larger than 4. So for here, I'm just going to come in and give myself sort of, this is my breaking point here. Let's make that a little bit straighter. Here, this is my breaking point here. So I could go ahead and plot both of these lines and -2x plus 8. So here is my 8, and I'll go down to over 2, and I could go ahead and graph, oh, that's not what I wanted to do. Continue going down to over 1, down to over 1, down to over 1. I know that this will only happen for x values that are smaller than or equal to 4. So here what I can do is sketch in this line, and I know that this line will really only exist for values that are smaller than or equal to 4. So I can actually erase all of these pieces. And since it's equal to, I can put a nice point here. So everything that's bigger than 4 will act as the line 1/2 x minus 2. So I can come in here, and let's graph this in a different color. Here's my -2. Up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, up 1 and over 2. So now what I want to go ahead and do is I can connect from here over, and if I take a look, I'll erase all of these pieces, and I want to come back. Since at 4, I'm really equal to this function here, which I represented in purple, I want to make sure that that purple representation sort of comes out on top. So now if I were to erase sort of my domain or my divider there, this is what this piecewise function will look like. So let's do one more example so we can sort of get, you'll notice here on the bottom of the slide it says continuous versus discontinuous. So a continuous piecewise function is one that I can start graphing, and I don't have to pick my pencil up off of the paper, which means that every x value is accounted for in a nice and smooth motion. So let's take a look here. It looks like my breaking points are here at 1. So there's one there at 1, and there's another that's here at 4. And I know that in between 1 and 4, the graph that I'm talking about here, so here I'll just put a purple dot next to this, we'll graph this in dot. I'm just graphing g of x is equal to 2. So at 1, I am equal, and I am going to go ahead and go over to 4. And at 4, I will have an open circle there because I'm not quite equal to 4. So from 4 on, and we'll do that in red, I am graphing x minus 5. So here's my y-intercept at 5. I'm going up 1 over 1, up 1 over 1, up 1 over 1. So here I will graph this line for all of my x values that are larger than 5. And what I'll go ahead and do is I'll put a solid circle here. I can erase the rest of that graph there. And here I will go ahead and sketch in this line that I have. And I'll go ahead and erase that domain piece since we're finished with that. Let's grab a nice green color. Everything that's smaller than 1 will act as x plus 4. So here is my 4, and I am going up 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. And I am going to go ahead and sketch this in nicely I also know that here, I'm going to go ahead and erase this, and I'm going to have a nice open circle here since I'm not quite equal to 1. So I can come on in and sketch this here. So if I go ahead and I look at this graph, for all of my x values that are smaller than 1, I act as if I am x plus 4. For all of my x values that are equal to 1 but smaller than 4, so equal to 1 but smaller than 4, I act as if I'm just equal to, oh, you know what? It looks like I made a mistake there. I'm just going to take this whole thing and I am going to move this. Oh, it's not going to let me move it, is it? Let's delete this, and in my purple, I think I sketched that in at 1, and really I wanted to sketch it in here at 2. So there we go, that was my mistake. And everything that's larger than or equal to 4, so you see I have that red circle down there, that is going to look like x minus 5. So if we have continuous versus discontinuous down here, if I were to try and draw over this function, although my domain has no holes in it, my actual function is not totally smooth and what we would call continuous. So I can see that everything sort of does have a value where it belongs. So for example, when x is equal to 1, it does have a nice value that's here, but I need to make my y sort of jump, and my y sort of jump here. So it's not a smooth function. It's not quite continuous, but for domain purposes, we do have a nice continuous domain. So we can go ahead and we can sketch in one more of these. So it looks like at -2, and at +4, 4 was a popular domain value here, at -2 and 4, so x values that are less than -2, my graph will just look like it's at 4. So here I'll have an open circle, and here we'll just keep going that way. In between -2 and 4, so equal to -2, I am down here at -1, and I'm going to go all the way to an open circle that's at 4. And for x values that are larger than 4, larger than or equal to, I'm here at 2. So this will continue to sort of go on that way. And it looks like I did all of those in the same color. But again, this would continuous or discontinuous. This, I can't necessarily trace my whole graph without picking up my pencil. So although there are no gaps in my domain, we can't call this a continuous function. So there's a few examples about graphing piecewise functions. Here's another one that's a little bit funky with kind of a funky domain. If I take a look here, everywhere where x does not equal 1, I'm going to plot x plus 3. So here is my 3, and I'm just going up 1 over 1, up 1 over 1, up 1 over 1. And I could go ahead and sketch this in, except everywhere where this is equal to 1. And here I would just have an open circle for myself. So I would sketch this in, and I could sketch this in. It looks like this is still in highlighter mode. And here I have where x is equal to 3. You know what? I think this might be a typo on my part, guys. I think what I wanted to say is here, x plus 3 where x is not equal to 1, and 7 where x is equal to 3. I believe this is supposed to be a 1 right here. So when x is equal to 1, I'm up here at 7, and that's entirely my fault. So here, you know what, let's go ahead and sketch this in a little bit nicer with my pen. So here I'm down 1 over 1 all the way through, and up 1 over 1 all the way through. So this is what this graph would look like. And same idea, this isn't a continuous function, but we would say that it has removable discontinuity. So if I look, this sort of piece really would just fit so nicely in that little circle, but because I am making the jump, this is also not a continuous function. So we can also algebraically check for continuity by checking the boundary points, which we can see here. So if I look, my boundary points are 4. And what I want to do is I want to go ahead and plug in 4 into both of these equations. So -2, 4 plus 8, and 1/2 times 4 minus 2. So this will go ahead and give me -8 plus 8, which is 0. And this will go ahead and give me 2 minus 2, which is 0. And since they both sort of pop out at the same value, we would say this is continuous. Meaning where this piece ends, this one is going to immediately pick back up. So here, let's go ahead and test these boundary points. So 1 plus 4 is equal to 5. So this one will leave off in this boundary at 5, and this one will pick back up at 2. So this is non-continuous. This one is not continuous. So what I want you to go ahead and do is I've attached some problem sets for you about evaluating, so making sure that we're picking the right domain sort of piece of my function to plug my value into. And there are some graphing problems for you to also work on, so pay attention to the open and closed circles. So I want you to go ahead, work on some of these, and we will go from there. Good luck, guys.